Okay, I think that's set up now. Okay, so we're going to look at some more code in this example here, in this folder here. Okay, and we're going to look at this example called square. Okay, so the key idea that we're going to practice with is rotating around a point. So what we're going to do is we're going to start with a square. This sits like this. Okay. And the idea would be to rotate it around different points. So first we're going to rotate it around that point there. So we're going to make it rotate 90 degrees around that point there. And then we'll change which point it rotates around. So we're going to create an animation of a square rotating around. Okay. Now up here it points out that rotation can only happen around the origin. The OpenGL, any graphic system, only can rotate around the origin. I want to rotate around that point up there. So what I do is I take everything, translate it down here. So that would be a translation to the left by -1, down by -1. That moves that point there. Then I can rotate. Then I can move back up to there. Okay. And that's described here as there's a point CD. Now, here, the point I want to rotate around there. Let's actually choose a different idea here. Suppose I want to take the center point here and rotate it around this point here. Like that's not what we're going to do, but suppose this makes it easier to visualize. Suppose I want to take the center of the square and rotate the square up there. Okay, so using the notation on the screen, we want to rotate a model around the point AB in the model's coordinate system. So this is the point AB. And we want to rotate that point around the point CD in space. So this is the point CD. Okay, so I want this point to appear here and rotate around there. Okay, so what do I have to do? Take this point, move it to here, rotate, then take the origin, put it up there. Okay, right. So now the order is going to be, the tricky part is, in words I say the following: take AB, move it to the origin, rotate around the origin, then take the origin and move it over to CD. Okay, but the code is going to be written this way. Okay, why is the code written that way? Well, if I write a formula for it, it's a little bit easier to see. Here's a vertex in the square. So that's one of these 4 vertices. What do I want to do to that vertex? I want to rotate that, I want to translate that vertex by -1, -1. That'll translate, well, I'm sorry, by -A, -B. Okay, so if I put that up here as a comment, the idea is I'm starting with a vertex V. Okay, I want to translate it by the amount -A, -B. Okay, that takes this guy and pulls it over to here. Then I want to rotate it. So after I've done that translation, the cap block. Then this whole thing is going to get rotate by some degree that way. Okay. So actually, I'll just abbreviate it this way. I'll just say rotate. So I'm going to rotate it. Okay. After I translate it to there, then I rotate it. Then I have to take that and translate it from here over to here. So that would be translate C comma D. Okay. So translation times rotation times translation times vertex D. So I can write it this way. That's written more algebraically. Okay. So translate, well, start with the vertex V, translate it, rotate it, translate it. Translate the vertex to the origin, or essentially, if this is the vertex, I'm translating so it's centered at the origin. So I'm translating it by that much so it's essentially centered at the origin. Then rotate it around the origin. So after I translate it back to the origin, rotate around the origin, then translate back over to where I want things newly centered at. Okay. Now, now, why is it? So this is what we want. Okay. Notice that when you write code, you read this in formulas from left to right. So notice that the first thing here is on the left here. The middle one here is in the middle here, and the one in the bottom is on the right. The way OpenGL multiplies the matrices is that in fact, okay, if I actually started with this, what it's going to do is I'm really starting with GL load identity. So if I want, what I'm really doing is I'm starting with the identity matrix here. So I start with the identity matrix. Every one of these multiplies on the right of what came before. Multiply on the right of what came before. So I start with the identity matrix. Multiply on the right of the identity matrix, this guy. Then multiply on the right of this guy, that guy. Then multiply on the right of that guy, that guy. And then the vertex ends up being on the far right. So that's the way we read it. You read it from top to bottom, from left to right in the formula. Okay. As you read from top to bottom here, you read from left to right in the formula. Okay, so it's kind of quirky. See, the thing is, which one gets done first? When you actually execute it, this one's done first because it's the one that's closest to the vertex. So they're actually executed going backwards. That's not the way they're, way they're executed and the way they're written is different. Now, it's what this is analogous to is if somebody gives you three functions, f of g of h of 7. Which function do you do first? H. You work from the inside out. Okay, it's read from left to right, but it's executed from inside out. Same thing's happening here. It's really just this. This is translate, rotate, translate. This is the translate by negative AB, rotate. This is the translate by CD. Okay, so it really is just work from inside out. But people get real confused by this. This is one of the places that makes people get mixed up. You're so used to reading code from top to bottom, and you think, okay, the first thing I see in the code is the first thing I do. So you think, oh, I'm going to translate, then rotate, then translate. That's not what it does. It translates, then rotates, and translates in that other direction. Mm-hmm.
But the vertex is still defined before that, right?
Yeah, all the vertices. This is really going to be put in a for loop. Yeah, what this is really going to be is that there's going to be a for loop here. Over here, it's going to say for vertex V in model. Essentially like that. All the vertices have been defined ahead of time. Or it could be for vertex V in array. Yeah, for the vertices in something. So that you've already stored the vertices somewhere. So now you're going to iterate through the vertices and transform each vertex one at a time. So the vertices were defined ahead of time. Okay. Then you're going to execute on each, this for loop will be wrapped around, well, this for loop here, and it's really kind of tricky. Okay, yeah, funny, new shoes, I keep tripping over them. Yeah, and just, yeah, I stepped on my own toe, on my own foot. Yeah, yeah, okay. All right, so the way this works is this stuff all translates to one matrix. So you're building a matrix here. So this has all been predefined ahead of time. So really what you're doing is your for loop is you're building this matrix here, or another way to put it is I'm building a matrix. Then I say for every vertex, V equals M times V. That's another way to think about it. So all the vertices were defined up here. Then the matrix is built here. So this would be the equivalent of building the matrix. And then you're going to use this matrix. This is all one matrix. Then you're going to use that matrix on every vertex. So that's kind of the way, it's kind of weird because this is all being done inside the GPU. So the code you write, you have to kind of build a model for how it works. Because the way the code gets written and the way it gets executed is slightly different. So you could also, like, if in thinking of this as pseudocode, you'd say, start here, define vertices. Okay, so you define all your vertices. You define all your, but actually, it's actually not the way OpenGL does it. Yeah, we're not going to do it that way. That's the way we would do it. That's the way more modern OpenGL does it. It's going to actually look like this. Let's go look at the code. It's really weird how OpenGL does it. Okay, so let's look in a minute where the vertices actually come from. That it's really more like build a matrix. Now, build a vertex, apply the matrix. Build a vertex, apply the matrix. Build a vertex, apply the matrix. That's actually where I'm going to write it. So we're really going to write it in a loop, sort of like this. So it's just going to be while, okay, for whatever, it's going to be create vertex, apply matrix. Okay. It's really going to be something like this. Create vertex, apply matrix. But we're not going to write the code that applies to matrix. That's going to happen automatically. So all we're going to do is create the vertices. So we'll only create the vertices. We'll define the matrix. We'll create the vertices. We'll never write a line of code that says apply the matrix to the vertices. That just happens automatically. So it's kind of really hard. It takes a little while to get used to how to think about this because you're doing a combination of declarative programming and applicative programming. Declarative programming is when you say you declare something that should be done, but you don't actually do it. You just say, this is what I want done. So we'll write the code that creates the matrix. But then the matrix from then on will be applied to every vertex automatically. Then we'll create a vertex and the apply the matrix will take place automatically, okay? So here's what it looks like when we get down here to the code. Here's our display function. Okay. This is just going to set up some stuff here. Here's what we really want to do. Load the identity matrix. Here's those three translate, rotate, translate. Now, this is the one we did a minute ago. I'm going to want to rotate around this point here. I want to rotate the square around that point. So now AB is equal to CD. The AB and the CD are the same point. Okay, I want to rotate around that point there. So the AB moves to there and the CD moves to there. So they're just the same point. So then this is translate by where is it? Oh, I'm sorry. Translate by this, rotate, then translate in the other direction. Okay. So this is the one that translates you to the origin. This is the one that rotates around the origin. This is the one that translates you back to where you belong. Okay, if you read it from left to right in the formula, you read from bottom to top, translates up to the origin, rotate around the origin, translate back to where you want. Okay, then I call a function called draw square. Okay. So I create my this creates the matrix. And then I'm not going to apply it to anything. I create it. It's OpenGL owns it now. Then I call draw square. Okay. Then down here, we'll see why I made this a function, because we're going to keep calling it over and over again. Here's the function. The draw square is going to draw two triangles. And OpenGL is kind of a mess. There's the color for that vertex. There's the color for that vertex. There's the color for that vertex. I have to mix all this up. OpenGL, there is another way to write. We're writing the old-fashioned OpenGL here. The newer version of OpenGL makes this a little bit better, but it's also got its own problems. So this is the old-fashioned OpenGL, and it's notoriously mixed up. You can't just say over here, here's my colors, and over here, here's my vertices. You have to alter, because it's a state machine. When the color's that, every vertex from then on has that color. So there's only one color. OpenGL only knows one color at a time, the current color. So I can't say this vertex has this color, this vertex has that color. I have to say the current color is this. Now here's some vertices. Now I change the color and give you more vertices. So there's only essentially one color at a time. So now I want each one of these vertices to have a different color. So I have to do color, vertex, color, vertex, color, vertex, color, vertex, color, vertex. It's just because it's a state machine. Now, every one of these vertices is automatically multiplied by the matrix because it's a state machine. Once I've defined the matrix, the OpenGL applies that matrix to every single vertex. So I never write matrix times vertex. It just happens automatically. So up here, I say, this is what my matrix should be. Where is it? Here's where I say what the matrix should be. That now is in the state of OpenGL. OpenGL holds that matrix. From now on, until I change that matrix, it's automatically applied to every single vertex I define. So I never apply that matrix. I only define it. It's applied automatically. So then every one of these vertices is going to be multiplied by that matrix, which will do what I want. It'll take this square, rotate. It'll take this square, move it to the origin, rotate, and then move it back over to there. Okay. Now this is an animation. This display function, which is like paint component in Java graphics. It's called when it's time to repaint the screen. We don't have any buttons or GUI elements to respond to a GUI, so we don't have anything that's going to call this thing. So what we did is this thing is set up to, in the initialization, it creates an animator. It creates an animator on that window. And what that does is 15 times a second, it calls draw display. So we don't have a GUI, so since we don't have any buttons to reply to, we have the operating system essentially generate events for us. So the operating system is going to essentially pretend that somebody clicked on something or whatever, however you want to think about it. But this is going to create a frames per second animator. Every 15 times a second, it's going to call the display function on that drawable. Okay. So my display function is, again, this is part of the declarative. I wrote that function, I never call it. There's nothing in this code that ever calls that function, just like paint component in Java graphics. You never call paint component, it's called by the Java virtual machine. Similarly, we never call draw square, it's going to be called by the Java virtual machine. In our case, it's going to be called 15 times a second. Okay. Then each time it's called, it's going to, I'm sorry, not draw square, I'm what? The display function. The display function is going to be called 15 times a second. Every time it's going to be called, it's going to clear the screen. So it'll erase what was drawn the last time. It'll erase what was drawn the last time. It's going to draw an XY axis, just a XY axis on the screen, just to make it easier to see what's going on. So it's going to draw this black XY axis. So the XY axis is going to be, it's going to, notice I'm setting things, I'm getting rid of whatever matrix somebody left in the state. So I start by putting load identity. I want to make sure that I'm not drawing someplace weird on the screen. So just to be safe, I load the identity matrix. I set the color to be 0, 0, 0, that's black, and I begin GL lines. GL line draws line segment, line segment. This is the x-axis, this is the y-axis. So this just connects negative, this just draws the horizontal line and this draws a vertical line. So it draws two black lines, 90 degrees apart. Then that ends that, okay? Then I'm going to think of this as I created a variable called frame number. So I can keep track of how many times I've been called. Because I'm going to do a rotation, and the rotation angle is going to be depending on how many times you've been called. So on the first frame, 0 rotation. On the second frame, a little bit more rotation. On the third frame, a little bit more rotation. So there's a variable up here called frame number. And the display function, the last thing it does is increment the frame number. And then it divides it by 360 because I'm doing rotations. So I'm going to make my frame number always between 0 and 359. So I'm going to think of each frame as 1 degree. So I'm going to make things a little bit simple here. I'm going to think of every time I display the frame, I'm going to advance by 1 degree. So it's 1 degree per frame. Okay. So there's the frame number being advanced. Okay. And then if the frame number is less than 90, this is what I'm going to do for the first 90 degrees of my animation. What I'm going to do is I'm going to rotate this guy 90 degrees. So I'm going to rotate this square 90 degrees. Then after I rotate 90 degrees, I'm going to change and do some other rotation for 90 degrees. Then I'll change and do some other rotation for 90 degrees. So right now it's only set up to do the first 90 degrees, and then we'll write the code for the other parts. Okay, so this is going to translate for 90 degrees around this point up here. Okay, let's just watch it. Okay, see, it's rotating around that point there. Okay. And then it did further. Now, if you want, now there's the 270 degrees left to go. Right now, I'm not doing anything. We'll block those in. But if you wait a minute, it'll do that. It'll start back to the beginning of the animation again. So it's pretty close to being back to the beginning. So now it's doing, now we got to frame 360, we're back to 0. Now that was frame 90, now we're at frame 91, 92. And so, so what we're gonna do is we're gonna fill in those other ones now, okay? And what I wanna do is, when this thing, now most of this green corner ends up down here, okay? So the green corner is going to rotate to here. When the green corner went here, I want to rotate around the green corner and rotate 90 degrees that way again. So rotate around the blue corner until the green corner ends up down here. Then rotate the green corner around this guy. So the idea is this thing will get down to here. And then that green corner will start rotating around there and bring the blue corner back over here. Okay. So let's draw a picture of that and figure out how that would be. Okay, so that's going to be the next 90 degrees. So what I'm going to do here is say, else if frame number is less than 180, here's what we're going to do. Okay, let's make sure we start with an identity matrix. Okay. Now we're going to do, well, I'm going to just copy and paste and then make changes. Okay, now remember, this is the, if we go back up to the top, it's CD, then minus AB here. So this is the C comma D. Oops. And this is the minus A minus B. Okay. At first, A, B, and CD were that point there. Okay. Now, after this thing is rotated 90 degrees, here's the point we're interested in. We'll switch to, we'll want this point here rotated around this point here. Okay. Okay, so after we've swung this thing down to here, this point's down here, we want to rotate this point around that guy there. Okay. So what do we need to do? We need to take this point and translate him down to here. Then we need to rotate him by a certain amount and then translate him over to here. Okay. So we're going to take this guy, and the minus AB will be -1, 0. We'll translate him down. Okay. Then rotate him, certain amount. We'll figure out what we rotate him by. And then we'll translate him over to here. The CD will be 1, 0. So he'll translate down, rotate, then translate over. Okay. Now the question is, what angle do we rotate him by? Okay. Now we started off over here. He rotated 90 degrees. Okay. Now we want to rotate him more. Okay. But that's what so the frame number should be the amount, it should still be frame number that we rotate by, because the frame number now would be 91, 92, 93. So that would be all the rotation that happened before, plus this a little bit additional rotation. So this frame number should still be, for our purposes, the right amount to rotate by. We're still rotating in the same direction. Yep. We're still, we started off here, we're rotating this way. Now we get to this point. This guy is down here, and now we want to just keep, we just want to like switch from rotating around here to switch to rotating down here and just keep rotating in the same direction. Okay, let's try. Let's see how this looks. Pretty sure this is the right way. Okay, there's the beginning part. That hasn't changed. Now when it switches to here, it should just start. Oh, no, I didn't do it right. Okay, it jumped. Okay, so we have to figure out what went wrong. Now let's see. Let's start it back up again. Notice it did rotate another 90 degrees. I probably got the order wrong. Okay, we want to rotate around this guy when it gets to here, but we're rotating around the yellow point. Well, notice we're rotating around the same place. We're rotating around the right place with the wrong corner. Do you see, what did I do wrong? We're rotating around the right place, but with the wrong corner. We got this corner down here. Yeah, see that corner down.
Yeah, because you change -1x instead of y.
Which one? Oh,
The-
which one? Which
The
line?
last line, both the places, I think.
Oh, let's see. Oh, okay. We need, oh, this needed to go down by -1. So the minus AB was down -1. And then CD was, oh, that one should be right. So the mistake was on this one. Okay, so that should have been the mistake. Okay, so now let's try it now. Okay, now when the blue one gets here, want to start rotating around the blue one. Let's just keep, let's just keep letting it keep walking. So when the blue one gets here, let's just keep letting it rotate around the origin with the blue one at the origin. Okay, now that'll mean that we'll need to take this guy, he's the blue one, and move him to the origin and just keep him there and rotate around the origin. So when the blue one hits the origin, we want to just keep rotating around the blue origin. Okay. Actually, what do you think? We rotated around this point, this point, yeah, then this point, then it's kind of like walking around the square, but okay, so now, we need another block of code now for angles be less than 270. Now, angle and frame number are the same thing here. I kind of kept it simple by keeping frame number and angle the same. Make sure we start with the identity matrix. Okay, now we want the blue corner down here. So we want this to be -1, here. Here. And then this one will just be 0, 0. Because once we've moved the blue one to the origin, we'll just stay there. So I'll go ahead and, I could delete that line, but just to keep things kind of easier to read, it's just that one. It's actually that. Okay, let's see if that one. No, actually, that isn't what I want to do, because now we're outside of the square. No, actually, what should we have done? I wanted to stay inside the square. Okay. We can do anything we want, but I was actually kind of trying to keep it inside the square. Let's see what would make let's see. No, this moved outside the square. Then back inside the square. Oh, this one moves us out of the square. Oh, we would rotate now around the top green one, right? Yeah, now we go to we would rotate the green corner around the green corner there. Okay, so we'll now be rotating around this point up here. Okay, so now I need another block. This is going to be frame number less than 360. This is going to be, we're going to be at this point up here. The CD is 0, 1. Okay, we're rotating around this point at the end. And I think it was this point here was being rotated around itself at that point. Let's watch it again. I think
that's the corner we're rotating.
Right. Okay. So then that would be 0, -1 here. Okay. So these are just CD and -AB are the same point. And if this is too slow, we can speed it up just by speeding up the frame rate. Like right now, I've got it kind of slow, just so we can make sure we watch it real easily. But okay, now rotate right. And then that green corner, when it hits the top, and we should be back where we started at this point. Yeah, see, and now it just is now it's back to where it started. So it just looks like a continuous animation because frame 0 and frame 360 is back to being frame 0. Okay. Okay. Now let's do a slightly different animation. Okay. What I want to do next is make the square walk down the line. Okay. Just make it like make the square, rotate, then rotate, just make it walk down the line as if it was like a square wheel. Yeah, you see people talk about bicycles with square wheels. Make this thing go down the line as if it was a square wheel, okay? And then what we'll do is after that, there's kind of a clever little, these are standard little puzzles you learn to do when you learn OpenGL graphics programming. So these are real common. The next one to do, let's make it walk down the line. And then the next one after walking down the line is have it grow while it's walking down the line. So actually have it be like he's growing. So the square will be rotating and growing, and then it'll hit that, and then it'll keep on rotating but growing as it goes along. So then we'll have to mix translations with scalings and rotations. Like right now, we're mixing translations and rotations, but no scalings. So when we want to make the square grow as he rotates, then we have to think about the rotation also. So what I'm going to do is make a copy of this. Call it square 2, and let's see if we can modify it to be okay. So let's think about we're going to do 90. It's going to first he's going to rotate around this 90 degrees, and then he's going to rotate around that point 90 degrees. So let's think about how this is going to work. Okay. So the first one's going to be the easiest one. So that's the first 90 degrees. So the first 90 degrees is we're rotating around that point. Okay. So that point just goes back to the origin, rotate around it, and goes back to there. So it's the point 0, 1. So for the first one, it helps to annotate these. So that's the CD. There's the negative AB, okay? The CD is the point that we're rotating around in space. So that's 0, 1. Oh, sorry, 1, 0. Okay, so, and then this would be negative 1, 0, because we're going to take that point, move it back to here, rotate them, then move them back over to here. Okay, all right. Oh, I forgot to change the name. So this is class 2 here, and I have to change it in another place. This guy instantiates himself. So you have to, these programs are messy to write because these programs are instantiating themselves. So when you change the name, if you don't remember to change it everywhere, you've got one program instantiating one of your previous programs, and you can get really confused. So I think those are the only 2 places. It needs to be changed at the top where it's named. It has to be changed here where it instantiates itself. Oh, first of all, I'm rotating in the wrong direction. Now we want to change the, I want it to rotate that way, just rotate down the straight that way. So I need to change the rotation. So now OpenGL does it like you learn in engineering and calculus classes. Positive angles rotate in the counterclockwise direction. That's standard out of calculus and engineering math. Positive angles are counterclockwise. Most people tend to think the other way around, but mathematics uses counterclockwise as positive angles. So all I need to do here is put a minus sign in front of, where did it go? Just use, the frame number is the angle, so just put a minus sign there. Okay, so the frame number is the angle, so I'm keeping it simple by keeping the frame number be the angle. Okay, so he's rotating there. When he hits here, we'll want to, we want him to keep on going. Now, first of all, we need to widen the screen. So another thing about us, like, how do I make this? Otherwise, he's going to roll off the edge of the screen. So how do I make the screen bigger? Okay. Well, right now, we haven't really mentioned this that much, but there's a nice little picture. Let me find the picture. This is one of the graphics books we've been using. And let's see if I can find the picture. This is how you usually think of a camera. I mean, that's how real cameras work. Real cameras act like your eyeball. The light goes into your eyeball, coming at, all the light comes into your eyeball, and that gives you perspective projection. But computer graphics systems can work in a different way. They can also work this way. This is called a parallel projection. There is no eyeball. This is what you use in mechanical drawing, and this is what you use for 2D graphics. Okay, what happens here is that everything is projected parallel to the screen. Instead of being shrunk, instead of being projected this way, okay, instead of being projected like this, things are projected straight across. Okay? You don't get depth perception this way. Parallel projection has the advantage, the disadvantage of parallel projection is you lose depth perception. But it's used all the time for mechanical drawing because it actually preserves distances. So like if you take a picture of a building, okay, there's a row of windows. If you take a picture of a building with a camera, the windows get smaller as they go along. Okay, well, that makes it hard if you're the construction people trying to build the building. You want to know, did those buildings actually, are those windows the same size or are they shrinking? So when you draw blueprints for building things, you use this kind of projection, because since it uses parallel projection, everything preserves its size. So if you took a picture of a building using this projection, there's a row of windows, the windows just look all the same, all the way across. The windows won't shrink as they get farther away from you. They just keep, all lines stay parallel. This is really good if you're just working in this front plane. If you're just doing 2D graphics, why not just use this projection and just stay in the front plane here? It's just easier that way. You can also use this one for 2D graphics. You just make sure you stay over here, but you have to know what plane you're in. Okay, so because if you move to the other plane, everything either grows or shrinks. So you have to be a little bit careful about what plane you're in. So what we're going to do is use this. This red square here is our stage. That's how wide our screen is. Okay, so right now our screen goes from -2 to -2, -2 to -2. Our screen, we're working in a screen that goes like this. It goes over here to 2, over here to -2, down here to -2, and up here to 2. So we only see that much of the world. What we want is a screen that's wide and not so tall, because we're going to roll this square down. So here's what we're going to do. Now, there's a function for setting up this red square. It's this function here. You give it the x, you say x min is the left side of that square. That's this left red edge. X max is the right. Most people usually call this left and right. He's being a little bit weird calling it x min and x max. Almost everybody calls it left and right. This y min, almost everybody calls it bottom. And this y max, almost everybody calls it top. Near is this and far is that. Okay. Anything in front of near doesn't show up in the camera, and anything past far doesn't show up in the camera either. Okay, so we're going to set this, like for example, we want the square to be able to roll down the x-axis. So we don't need left to be much. So let's see, go over here to where there's the call to ortho. That's done in the init function. The init function initializes OpenGL, so we're going to set the camera up just once. Okay, here's the call to GL ortho. Here's that function. I'll do -1 for left, but I'll make right, I don't know, 5 or 6. Let's give ourselves some room on the right. So there's 6. Then for bottom, -1, and for top, say 2. Because we want, when this guy rotates, he's going to rotate, when he rotates like this, he's taller than 1 unit high. He starts out 1 unit high, but when he rotates, he's a little taller. So we'll have -1 down here. And in fact, if I wanted to, I don't even need what's below. I could make bottom 0. We'll see what it looks like if I make bottom 0. Okay, so I'm defining what this box looks like. Okay, I'm defining what this, you can think of this box as your stage. You're setting what your stage is. So you're deciding what's the left edge of the stage, what's the right edge of the stage, what's the floor of the stage, what's the top of the stage. Anything off those coordinates are going to be chopped off. Okay, so let's just see what this looks like. I give myself a little bit of room on the left, a lot of room on the right. I'm going to chop things off right at the floor and give myself a little bit of room on top. Now what happened here? It looks real distorted. What did I do wrong? My stage is, wide and not very tall. But when I look at my screen, it's all smashed up. Why? There's a disconnect between this and this. This function sets the logical stage that OpenGL uses. But that doesn't determine the shape of my window. Who determines the shape of my window? Java and Windows. So I have to tell Windows to make the shape of my window match the shape I want this guy to be. I have to match these. Otherwise, this window gets smashed into this window here. Okay, so I need to make this window match the aspect ratio I'm giving this window. Now, let's look over here. What did I make it? Okay, let me close this. I made it, I have to think a little bit. I made it 7 units wide. So I made it 7 units wide, and I made it 3 units tall. Now, what would be an easy way to get a window that shape would be 700, 300. Just scale, they're just scale, 700 pixels wide and 300 pixels tall. So I've got 7 units wide. Oh no, 2 units tall. 2 units tall. Okay, so let's make our window, just keep things simple. It's not gonna look good. Let's make our window 700 pixels wide and 200 pixels tall. Just, that should give us the right. Now we have to find that in the code. That's created down here in main. Main sets up the window. And the window, does anybody see what line it is? I'm which one is it?
142. 142.
Yeah, there it is. So I want it to be, I think that's width and height. I think that's 700 wide and 200 tall. I think, okay. So now it's kind of weird. The logical stage is set by the OpenGL, but the actual window is set by Java, and it's up to us to get those guys in agreement. And this is one of the tricky things about graphics programming. You kind of think that once you set this, the window would match it, but that's not the way it works. The window's its own entity. This is just what OpenGL is using, and it's up to you to make sure that the shape of this and the shape of your windows match. Okay, so now, see, now notice the square is a nice perfect square, and he's kind of walking down that. Okay, so now we can do the next step. Now let's get let's see, now let's think about what the next step should be. Okay, so the blue corner is going to be over here at 2. This is 1, 2. So we want to rotate around. The blue corner started in the upper right-hand corner. We want the blue corner to start rotating at 2. Okay, so we're going to be rotating around the blue corner, but over here at 2. The blue corner will get to there, and now we want to start rotating it there. Okay, so we go to, now this is going to be the block of code for 90 to 180. Okay, so here's the point. This is the point that is the CD. So this would be 2, 0. Okay, so that's the point CD. Okay, now this is the point that we want to rotate around that point. So that was this guy here, that's one, so that's -1, -1. So this should end up being -1, -1.
Positive one x, right? It's already at 1, we have to move it to 2.
No, he's actually sitting over here. He's not been moved over there.
So it's 1, 1 right now, right?
Yeah, this is 1, 1.
So 1 from moving, we come down by 1, so 0,
Oh,
1.
wait, okay, wait. So he needs to, he moves over here, rotates, so he's gonna move, all right, he's gonna move from here to here. Oh, yeah. He's gonna move from here to here. So to move him from here to here, you move him from, you,
1 down and 1 right.
no, let's see. No, the way these formulas are set up, no, but we have to think, the way the formulas are set up,
Center.
it's not the distance to that point, it actually is the point AB. It's not the delta from here to here, it's what is that point there. Yeah, it's not the delta. If you look at remember, the idea was start here, take him, move him to here, rotate, then you move him, the origin, to there. So it isn't moving him to there, it's moving the origin to there. And so you have to, so you move him to there, that's a delta, and then you move him to there. So that's the point we want to rotate, that's the point in the model we want. We move that point to there, then we rotate, then we move that point to there. Okay, so over here, that should be, this is the moving to the origin, -1, -1. Then we need to rotate them. These frame numbers should be negative because we're now reversing the order of rotation. And then after we've rotated, the origin goes over to here. So the origin will go translate by 2 to the right. Okay.
One thing, when the animation runs, why you only see the rotation and not the translation?
Oh, you are, because it's rotating around someplace else. See, the translation is built in to this. See, when I make something rotate around this point here, that's this, you're not supposed to see this guy move, rotate, move. The whole point is you see him as if he's moving around there. You're making him move around there by all, this is all happening before the things are drawn. Before anything gets drawn, all these vertices are multiplied by a matrix to move them over here. Then they're multiplied by another matrix to rotate them. Then they're multiplied by another matrix to move them over here. Then you draw them over here. So you only draw them when they ended up over here.
Could you technically see that happen if you put that draw square after every?
Yes. Yeah. You could do it. You could say, okay, you would essentially say, rotate, draw it, translate, draw it, rotate, draw it. And I did that in one of the other classes. I did that. It's a bunch of code to do it, but I actually did it where I would like make it look like a light gray. So that, how the idea is that when you want something to, you want to show a shadow of something, you do it in. So it's actually not that. It's just a bunch of code. But yeah, you can literally just do but it's hard to do in OpenGL because here's what you'd have to do. It's a real mess to do that in OpenGL because remember the matrix is made first. Oh, actually, what you would do, that's why I put it in a function. So what you would do, you would say load identity, draw square, translate, draw square, rotate, draw square, translate, draw square. Yeah, that's why I actually put it in a function. So actually, we'll try it. Let's see if we can actually do that. But right now, it'd be nice to have the colors change. Let's see what happens. Let's do it on this one. That should draw the original square. You have to make sense of it now. Well, yeah, what should we have done? We probably should have. Either you have to like make them get lose some of their color as they move, or draw them and erase them real quick. Because what's happening now is they're getting drawn and they're just sitting there.
Can you put one more draw square after the last translation?
It's there automatically, because it's after the if statement. Yeah, that one, that's why I didn't put the, because it's after the if statement.
Or we don't see it moving to origin, right? It just moves from the rotate to the.
Well, the trouble is it's gonna just be it's just gonna be more stuff on the screen that'll be really hard to interpret. Yeah, that's the trouble. It's a little bit tricky to create nice animations of these things. Let's see, how far have we gotten now? How far down this line? Okay, we've got the first 90 degrees. Now, now we're gonna want to rotate the green square around 3. Okay, so the green square, which one is the green one? Oh, let me see. This is this is red. This is red. Oh, this was green. This is blue. And this is yellow over here, right? Okay. And we want to get, now we're going to want yellow around 3. Okay. So now we're going to want around 3. We're going to have
Green around 3, right?
no, let's see. Oh, it's green?
Yeah.
Oh, yeah, green. Yeah, we started at yellow and then we did blue. Now, yeah, green. Yeah. So we want this guy rotated around 3. Okay. So this is the next these. So we're rotating around 3 here. No. And this one is now green, so it's 0, -1, right? Oh, I forgot to change, yeah, okay. Now, okay, then what will be the next one? The next one will be around 4. And it'll be the, yeah, so this one will be
Negative frame number.
and negative frame number, okay. Now, this is a simple animation, but when you actually learn how this kind of stuff happens, you see that there's a fair amount of math going on. That's a trivial animation, but there's there's no other way to do this. It isn't like games have some magic way to do this. They're doing this kind of arithmetic. Okay. Oh, and the way we have it now, it just goes back to the beginning. It just walks down. So now it's going to walk down the line 4 steps and then go back to the beginning each time. We could have it just keep walking down the line, but we can't have an infinitely long line anyway. Now let's do another version of this. Let's see if we can make it grow. Let's make it grow. Okay. This is a little bit trickier. So let's do a version 3 now. Let's see. Let's at least do the first step of it. While he's rotating around yellow, in the 90 degrees he rotates, let's have him double in size. So now that means that he'll land on 3. Okay, so as he's rotating, he's going to be doubling in size, so he'll end up landing on 3. Then we'll worry about the next step. Okay, so the question is, how do we get something? So we're going to still rotate around here, But now the question is, where does the scaling go in our code? Okay. Remember, things don't commute. Order matters a lot. Okay. We want this guy is we're in this block of code. Okay. So we're going to use the scaling function. So think about it. Should we scale first? Okay.
I know.
If you scale, well, okay, first of all, what do I mean by first? Okay. Right now, our code looks this formula here. So let me write that down. Because if you use the word first, do you mean first from the point of view of left or right? Do you mean first from the point of view of which one you apply? If you talk to programmers, they use the word first when they're talking about graphics. If half of them mean one end and the other half mean the other end, you get all mixed up because both are first. This one's first on the line, this one's first applied. Okay, so let's think about what we mean by scaling. Should we put the scaling like right here? Or should we put the scaling, over here? Yeah. So, which place should the scaling be? Okay. Think about it. Let's try it from this way. Suppose I scale him. Okay. But then I move this point to the origin. I'm not rotating around the corner anymore. Okay. So if I scale, see, this one starts by scaling, but then it translates the corner AB back to the origin. But then after you scale, that AB is moved away. So we could probably make that work, but it's going to be confusing. Okay, so that's not probably where we want the scaling. Okay. Now, what if you leave it where it is over here? Okay. So you take this guy, you're going to move him to the origin, rotate him, move him to where he belongs. Okay. And then at the last step, scale him. Because he's where he wanted to be, but that doesn't work either.
No, it will be direct 2, not 3.
If I'm right there and I scale things, I move away from the origin. Scaling moves you away from the origin. Yeah. Suppose I draw a box like that, and I scale everything by 2. That box grows to be twice as big. Okay. But suppose look at this box here. Now grow everything by 2. This box gets to be twice as wide and twice as tall. This box gets to be twice as wide and twice as tall, but he also moves twice as far from the origin. So this guy not only scales, but moves. This is one of the tricky things about scaling, because you're scaling everything in space. All of its space is expanding. The thing about scaling is like rotation. You can only rotate around the origin. You can only scale about the origin. You can't scale him by himself. Just like you can't rotate him, you have to move him to the origin, rotate him, then move him back. Same thing is true with scaling. If you want him to, suppose you want him to be right there, but you want him to be twice as big. You actually have to move him to the origin, scale him, then move him back to where he was. Just like rotation. So because scaling like rotation happens, the universe just expands away from the origin. Just like it rotates around the origin, it expands away from the origin. If something's centered at the origin, it just grows with expanding space. But if something is not at the origin, not only does it expand like you expect it to, but it shifts away from the origin, which you may not have expected. Okay, so what would be the best way for us to grow our square?
Move it to the origin, rotate, scale it. And then
Let's try, yeah. So when it's at the origin, let's do the scaling and the rotation at the same time. So that would mean we would look something like this. That would be like either, let's say, right after the. Okay. Let's try that. So it'll be, now, if we're reading from left to right, like the code would go, okay, be translation, scale, rotate, translate. So translation, scale, rotate, translate. So let's put the scaling right before the translation in the code. So up here, that would be GL scale. And scaling is done by, I'll just leave. You actually have an X scale, a Y scale, and a Z scale. You can scale in all three directions. You know, you can, now what we're going to do is we're going to do uniform scaling. We're going to make the X scale and the Y scale the same and just make it. Now the other thing we have to do is each frame, he's supposed to scale a little bit more and a little bit more and a little bit more and a little bit more. So we're going to have to figure out a formula for that, because he's not just going to scale by 2, because that, that'll make him just pop up.
Yeah, that'll make it should
Pardon?
if it was just like that, it would scale twice every.
Well, we're resetting it to the identity though. Oh, yeah, see, but we're not accumulating the scaling. We're setting it, if you didn't have that identity, then it would just keep doubling in size. Okay, so the scale will come before. Okay, now the question is, what do we scale by?
The frame number
Well,
by some constant.
as we grow by 90 frames, we want to grow to 2. So it looks like this. Here's a simple way to do it. It turned into a little algebra problem. Okay.
You also have to add +1, so it doesn't.
Here's 90 frames, and here's scaling. So we want this to grow like that. It's just y equals mx plus b. Okay. No, actually, I'm sorry. We start at 1. That's the formula we want. Yeah. If you think of it as an equation, the scaling starts at 1. Okay, so it's y equals mx plus b. The intercept is 1, and the slope is delta y over delta x. So the slope is delta y is 1, and delta x is 90. So it's just 1 plus x over 90. And x should be what? X is the frame. Okay. So it should be frame number divided by 9, 1 plus frame number divided by 9. So let's just try it real quick. So this would be 1 plus frame number divided by 90.0. And make sure everything's not, we don't want to do integer arithmetic. These are supposed to be floating point numbers. And z scale will just keep it at 1. To the z direction, we won't change. Okay, let's just give this one a try. Oh, what did I do wrong? Oh, first I've changed the name. And I've changed the name in 2 places. Oh, wait a minute.
Oh,
Oh, I
you're
opened.
writing it square 2.
Yeah. Okay. Now I think this is what I want. Oh, I have to tell it. You have to,
Does Z need to be a float as well?
pardon me?
Does the Z have to be a float as well?
Well, yeah, and also I didn't tell it to use floats. So where was that? That's scale. I am using I'm using doubles here. So I forgot. I'll go ahead and use doubles here. Okay, so I'm doing the other ones with doubles. So I'll do this one with doubles. Cool, okay, yeah, we're out of time, but the next thing now is to start, now rotate around, well, rotate around 3 of that corner that landed on 3, and just keep making them rotate and grow at the same time. Okay? And it's just, this is the kind of coding that, this is what you'll be doing in the next homework assignment. Okay, so now it'd be, right around that point, make it grow and keep rotating. Okay, we'll quit there. I'll put these examples up on the website after class. How do you end recording?